Hello, everyone, and welcome to your lecture on sedimentary rocks for Earth Science. We're going to be going through the record of Earth history, basically, because most of Earth history is recorded in the sedimentary rocks. So we'll be going through, first of all, what makes sedimentary rocks so important for learning about Earth history. So that's your first question on your lecture assignment, and we'll be going through this, our slow march through the different rock types. So, we covered igneous rocks last time, and we're going to be talking about sedimentary rocks this time. We actually aren't going to cover metamorphic rocks in this class because I think that's just a little bit too deep into rocks, and we need to go for our Earth Science class. But we can just start off very simply with what are sedimentary rocks, and they really kind of have I think, in a way, a frustratingly vague definition. Because really sediment can be a lot of different things. We're going to see that a little bit here. But sedimentary rocks are basically rocks that are made up of, I put here weathering products, but it can even be more than that. Any really loose material that can get consolidated into a rock can become a sedimentary rock, and we're going to see that as we move through the class. And they also, importantly here, I note, provide a record of past environments on Earth's surface. So sedimentary rocks are mostly superficial rocks. They're occurring at the surface of Earth's crust, not really deep into the Earth. They're not in the mantle, they're not in the core or anything. They're on the very top of the crust. They're not even in the deep crust even. They're on the very surface of the crust. So we'll get more into this. As you see, this picture here shows you a lot of the crust is, you can see these kind of stripedy rocks here, trying to show the layering. Those are the sedimentary rocks. Sedimentary rocks often have strata or layers, okay? So the surface of the Earth, about 75% of it, you can see up here, is covered by sedimentary rocks. But as a matter of volume, like how much of the crust is actually made of sedimentary rocks by volume, or maybe even we could say by mass, that's only a really small percentage of Earth's crust. It's only really, I don't even know what that is, 5% or something like that, maybe between 5 and 10%, 7%, something. It's a very small percentage that actually consists of sedimentary rocks. The vast majority of Earth's crust, and we're just talking about the crust, we're not even talking about the mantle and the core and all that other stuff, is composed of sedimentary rocks. Okay? But it covers a lot of Earth. Okay. And another thing I wanted to point out here is that sedimentary rocks are often, if not always, stratified. So I can even get a little rock to show you. So I just got to pop myself up here a little bit bigger so you can see this. But I just want to point out this is sandstone. And if you look up close, I think you can see pretty clearly the different layers in there, right? So you could see the different strata. You could see that over time you had layer of sandstone, little layer of sandstone, millimeter at a time. Maybe it's just, and those might be like yearly, almost like tree rings, like yearly deposits of sand from whatever. So anyway, that's what I mean when I say you can have these strata present in a lot of sedimentary rocks. It's a very common feature. Okay, so now let's go on to this first question, because it says, what are some things that sedimentary rocks can tell us about Earth history? Well, one of the main things is that sedimentary rocks tell us about the environment of deposition at the time. Different environments deposit different kinds of sediment. So, some of this stuff is, really obvious. Like, if you're at a beach, and this is not a trick question, a coastal environment, you're a beach, what kind of sediment do you find? Well, probably, you find sand, right? So you go to the beach, you see sand. Over time, that's going to become what kind of rock? Again, it's not rocket science here. What kind of rock do you find? Over time, you find a sandstone, right? That sandstone is created from sand. And it could be a beach sand, but that also there are other environments that create sand, right? So you might know in a desert, right, you can get sand. We geologists actually have ways of looking at sandstone, looking at sands from sandstone, determining whether that was a desert environment or whether it was a coastal environment. But, the main point is all these different environments that you see up here, deltas, like think of like the Mississippi Delta in Louisiana, Mississippi, reef environments, sand dunes, saline lakes, fluvial environments mean like rivers, swamps, right, lakes. All these different kinds of environments leave different kinds of sediment and therefore different kinds of rocks. So when we go and we find rocks I want to show you another example. I'll use this example a lot. I'm going to get big again. Here's a limestone. Limestones, and if I put this up to the camera, you can see this is filled, and you're probably like wondering, what are those little weird indentations? Probably you can't see those too well, but they're shells. Those are shells for like seashells, right? So this is a limestone actually made in a reef environment, like a coral reef almost. But I found this in Tennessee, right? So it shows you that at one time, what does that mean? Tennessee was underwater and it was covered by a reef, like by shallow water in a reef. So it shows you that the environment has changed a lot in Tennessee over time. Now it's whatever, it's like a forest, but it used to be a reef. It used to be underwater. Okay, so we learned about let me get the PowerPoint back up. We learned about the environment of deposition, what kind of environment was there at the time. Limestones, actually a lot like the one I showed you earlier, those limestones are formed from reefs. And it could be a coral reef, but there are things that make reefs, like oysters, for example, make reefs. And there are other animals throughout Earth history that have made different kinds of reefs. Sand dunes, like I already said, make sand. They make sandstone. Okay, so they indicate the environment of deposition. But they also tell us, like I showed you with this hunk of limestone, actually there's kind of almost everything that I want to talk about in what we learned about Earth history is contained in this one sample of limestone, because it also tells you about sea levels, right? So we get to know a little bit more about what we call paleogeography, about what were the coastlines and the continents, what were they like, where were the sea levels at different points in Earth's history, because we can look at this and see, okay, well, Tennessee was underwater. And actually what we find is Texas has been underwater for a lot of its history, and actually has a lot of limestone. In fact, by the way, a lot of the building stones that you might see around town and around San Antonio and in Austin, a lot of them are limestone from the Cretaceous, when this little guy was walking around up here. You can see this dinosaur, and that's another thing I want to talk about too, is we also know not only about depositional environments, we know about sea levels, we also know about past life. So fossils are preserved mostly in sedimentary rocks. Again, I go back to my limestone sample. You can see all of the brachiopod shells in there. We have some knowledge of past life and how life has changed on Earth from the sedimentary rocks. Okay. Another thing that I want to hit on here too is we also know about climate from looking at sedimentary rocks. Sedimentary rocks actually preserve a lot of information about what the climate was like at different points in Earth's history. So I won't go into all the details about that in this class, because it's just kind of an intro class. If you want to learn more about that, you'd have to take historical geology. We got all into the nitty-gritty details of it. But we can learn about Earth's climate over Earth history from sedimentary rocks. And that's really important because, you probably heard people saying Earth's climate is changing. There's climate change. Well, is that unusual compared to Earth's history, or is it the normal pattern of things, or what? We have to look at sedimentary rocks to answer those kinds of questions. Okay. And finally, like I said, we learn about the very interesting past life that has existed. Probably you're looking at some of these animals, you're like, what even is this? What am I even looking at? But these are some of the interesting animals that lived in the Cambrian period that look very foreign to us now. So we see that we can get from sedimentary rocks a whole history of Earth's past life and how life has changed over the years. Okay. So that's the answer to number 1 right there. Now let's go on to this messy question number 2. which is really kind of it's a complicated question. And even though it seems so simple, what is sediment really? And what are the kinds of things that can constitute sediment? What that means, like what makes it up. So sediment really can be anything. It could be any loose material that can consolidate together to form a rock. Normally there are around 4 things that will normally constitute sediment, okay? Although it can be a lot of different stuff. The norms, there's 4 different things, okay? So the first one, I have them all listed here, A, B, C, D. But the first one here are just loose fragments of rocks or minerals that are broken off the bedrock. So we're going to learn about weathering later. But these are just the loose bits and pieces of broken rock and mineral that get snapped off, broken off of the crust, and they become loose material. And once those rocks are loose, they're no longer attached to the crust, you are officially sediment. Okay, so and even if it's a big old boulder, you can see some of these things are really big, and some of these things are small. But even if it's a big old boulder, we still call that sediment. Okay, so that's one thing. Another thing that can constitute sediment are shells or shell fragments. And one thing that I want to emphasize here is that although definitely, like I've shown many times, you can see the shells that make up this rock, but the fact of the matter is a lot of the shells that make up sedimentary rocks are microscopic. You probably know that there's a lot of different kinds of plankton that live in the ocean. But more importantly, those plankton species create their own little shells. They are teeny, tiny, microscopic shells. I have pictures. These are electron microscope image pictures. You actually need an electron beam to scan and image these things because they're so small. A lot of them are smaller even than the wavelength of light. So you can't even see them with a normal light microscope. They're really, really tiny, and yet beautiful little shells. These are actually shells made of sometimes calcium carbonate, sometimes they're made out of silica, like quartz, but in any case, they are little teeny weeny bits of mineral content. And what happens is over millions of years, these little guys live, they die, they make their shells slowly drift to the bottom of the ocean, and they can accumulate and become sediment and sedimentary rocks. And I want you to just think about this. I know this seems like almost mind-boggling, like, wow, you would need trillions and trillions and trillions of these to make a rock like this, right? And yeah, that's the truth, right? So even if the sediment only collects 1 millimeter per year, 1 millimeter is like as thick as your pencil lead, right? So let's say they only collect 1 millimeter per year. Well, over 1,000 years, you have a meter of sediment. And over 1,000,000 years, you have a kilometer of sediment, and that can easily become a sedimentary rock. Okay, you have enough pressure and temperature at that point to bury it a kilometer deep. You have enough pressure and temperature to make a sedimentary rock at that point. Okay, so that's another big source of sedimentary rocks that creates the limestone. A lot of the limestone family of sedimentary rocks are created through shells, shell fragments, these little teeny weeny things you see up here. We actually call these tests, okay? Tests. All right, another thing are from mineral precipitates. I'm going to show you a little thing here I think is pretty interesting. So I got 2 beakers here. Actually, let me pop myself back up here. Okay, so I'm big now. I'm going to take 2 beakers and I'm going to pour in here some different mineral-rich fluids, okay? And you know that a lot of minerals, we discussed this in our mineral lecture, a lot of minerals can dissolve in water, right? And a lot of natural water, groundwater or even rainwater or stream water is really filled with a lot of dissolved mineral content. So if I take these 2 beakers, you take a look at this, and, I guess this looks a little bit cloudy, but it basically looks like clear water, right? But if I mix these 2 things together, you can see that I get a white fluid. That white material that you see here is calcium carbonate, calcite. It's the exact same stuff that makes this sedimentary rock. So I'm going to put this beaker up here and out of the frame, and you're going to see that by the time we get to the end of the lecture, it'll already have kind of settled out. The minerals have kind of settled out and settled on the bottom, and when they settle on the bottom, they make a sedimentary rock, and that is another source of minerals for sedimentary rocks. We call those precipitates. Okay, so when minerals precipitate out of, oops, I'm showing you the wrong thing. When minerals precipitate out of a fluid, we call that a chemical sedimentary rock. Okay, so we have the clastic sedimentary rocks. Those are made out of little bits, right, of rocks and minerals. We have the biochemical, these are called biochemical sedimentary rocks. They're made out of shells and shell fragments of marine life. We have the mineral crystals that precipitate out of water. We call those the chemical sedimentary rocks. And then, of course, we just have plain old organic matter. You know, think of all the, like, just the plants and animals, materials, organic material that, you know, plants and animals die, their bodies are slowly decomposing, but sometimes that material can get integrated into a sediment, and sedimentary rock can be preserved for the future, and that's how fossils form. But it's also how fossil fuels form, you know, like coal. The main way that coal is formed is an environment like you see up here on the screen, in coastal swamps. Actually, a lot like what we have here in Corpus Christi. We have a lot of coastal wetlands, marshlands, right, that are actively preserving a lot of that organic matter that's present. And boy, I know when you're at the bay, you can smell that organic matter, right? It's a lot of that sulfur rich. You can smell the bacteria breaking down the organic matter in the soils and the sediment. That's a lot of times what you smell. It's kind of funky smell when you get near the water in the bays, in the back bays. I know sometimes you're crossing over the JFK Causeway over towards the island, you can smell that. But anyway, that's what you're smelling. You're smelling the organic matter and the sulfur being released from the bacteria breaking down the organic matter in the soils and sediments. Okay, so anyway, those are the things that can constitute sediment, and that gives us the four types of sedimentary rocks. Okay, so let's go on to question number 3. What are the processes that generate these kinds of sediment? So this kind of material, the clastic sedimentary rocks, are created by, the process is weathering. It's the breaking down of, and we're going to have a whole lecture on weathering next lecture, but it's the breaking down of the bedrock to form, the weathering of the bedrock forms the clastic sediment. Okay, so for number 3, this is where the processes generate those kinds of sediment. Clastic sediments generated by weathering. Okay, what about biochemical sediment? That is created by marine life. It's created by, you could just say something like, you know, marine biological processes or something like that. Or you could just say simply marine life, right? Marine life is what creates that biochemical sediment, the tests and the shells that get preserved in the ocean. What creates this material? It's this process, right, that I showed you. That's called precipitation. So precipitation, and also another thing that plays a role here is evaporation. You could imagine if I left this beaker out for a month, all the water would evaporate and I'd be left with the chemical precipitates at the bottom, right? So, and that would become a sedimentary rock. So that's precipitation and evaporation. That's the process that creates these kinds of what are called chemical sedimentary rocks. And then you could just put kind of organic processes or biological processes that create the organic matter that creates the organic sedimentary rocks. Okay, so there are your beautiful clastic sedimentary rocks. They're made out of broken pieces of, these are now number 4 of the 4 basic categories of sedimentary rocks. First one's clastic. So we have the clastic sedimentary rocks made out of the broken pieces of the crust, the sand, the silt, the clay, the boulders, the pebbles, all the stuff that gets broken off of the crust, the bedrock, and conglomerates into a solid rock, right? So you see different types here. You see a sandstone, obviously made out of sand. You see a shale, which is made out of mud, right? So when mud gets preserved, it becomes a shale. Conglomerates, you can see, are made out of pebbles and gravel. Breccia also is made out of broken, more angular pieces of gravel. Maybe not so much pebbles, but more gravel. Okay, so we have different names. And actually we give different names to different clastic sedimentary rocks on the basis of grain size. So if the grains are very small or if they get progressively larger, then we give it different names. Okay. Biochemical sedimentary rocks, some examples of that are limestone, chalk, chert. This, amazingly, chalk. Look at these beautiful white chalk cliffs. These are the famous white cliffs of Dover. They are made, this is just mind-boggling, these are made almost entirely of these little planktonic organism shells. They're tiny, totally microscopic, and they have a cute name. They're called coccolithophores. Coccolithophores. So coccolithophores, which are single-celled planktons with a carbonate shell, and they build up over time chalk. So these hills that you are not hills, but these cliffs that you see here, these very iconic cliffs, are the white cliffs of Dover. Totally chalk. It's all made out of chalk. Okay. Chert is made out of the shells of plankton that instead of making their shells out of calcium carbonate, they make their shells out of silica. Okay. I do want to show you, just remind you that a lot of marine organisms, I think I showed this to you before, but you may don't remember, but a lot of marine organisms, like this clam shell right here, okay, make their shells out of calcium carbonate. And remember, we can always test for presence of calcite, calcium carbonate, with an acid test. So if I put the acid right up here, and I can show this to you. I know the lighting's not really good, huh? We need better lighting. Oh, you can hear it fizzing now. I don't know if you can hear it, but I can hear it. But this calcium carbonate shell, it is fizzing and breaking down with the acid. So calcium carbonate will also break down in acid. If I take this limestone that I showed you before and I drop the acid on it, let's see if we can see this more clearly. And I'm kind of trying to show this to you, but I'm trying also not to drip it on my computer. Whoops. But anyway, it is fizzing. I need a better camera, don't I? And I also need to now clean up my computer because I spilled acid on it. So there we go. Coffee filter will do. Okay, that's all right. I'm actually replacing this computer this week. Not because I dropped acid on it. It's because it's 5 years old now. Okay. So anyway, let's get back to the lecture. I'm trying to show you something cool, but it's not looking too good. Okay, so those are the biochemical sedimentary rocks. You can see number 5, it's asking you give examples of each of these rock types, right? So clastic rocks. What are some examples of clastic rocks? Sandstone, shale, conglomerate, breccia, even more siltstone. Those are all different clastic sedimentary rocks. What are some examples of biochemical rocks made out of shells and tests of marine organisms? Any of the limestones, chalk, coquina, then also chert. It's all made out of marine organism shells, basically. All right, what's the next group? There's coquina. I think coquina is a really amazing rock. It's really just, look at it, it's just a bunch of shells glued together, like macroscopic shells glued together. And by the way, a lot of coquina forms in Corpus Christi. Limestone is made of a mix of calcite-rich mud and shells, just like I showed you. Doesn't that look a lot like this rock I keep showing you from Tennessee, right? It's that gray kind of mud color. I'm trying to spill acid on myself, and I'm not being successful. Let me get another little coffee filter to dry myself off with. Sorry. I'm only using coffee filters because I have them here and I don't have a napkin. I drink too much coffee, I guess. There's the beautiful chalk, White Cliffs of Dover, made of those little microscopic coccolithophores. Okay. So there you go. Those examples of biochemical sedimentary rocks: chert, limestone, chalk, coquina. Lots of examples there. How about chemical sedimentary rocks? Those are the rocks made up of precipitated, evaporated grains. You get things like travertine, dolomite, halite, rock salt, gypsum. I'll show you some more pictures of these later, but these are all examples of chemical sedimentary rocks. Okay, the final one, what about organic sedimentary rocks? Organic sedimentary rocks, the main rock of that family is coal. So coal is a rock that is made up of vegetation, which over time is heat distilled. So I'm trying to find my little, here it is. Okay. It's heat distilled. So we start off with, we start off with plant and vegetation matter. Heat and pressure start to squeeze out the more volatile elements, and over time we get various grades of coal. So the first grade, which is like the dirty coal, the quote-unquote dirty coal, is lignite right there. Then we get subbituminous, bituminous, and finally anthracite coal. Anthracite coal is kind of the clean coal. It's almost pure carbon without almost anything else in it. It's just pure carbon, and it breaks down very high temperature, and it's pretty clean. Of course, it releases a lot of CO2, but besides that, it's clean. Okay, organic sedimentary rocks. Also, you could also consider oil shale to be an organic sedimentary rocks. Oh, sorry, here are some pictures I wanted to show you of the chemical sedimentary rocks. Gypsum, rock salt, dolomite, travertine. These are all, and I mean, you can literally see the travertine here in this picture being formed at a hydrothermal vent, right? So this is like a hot water spring, hot spring, right? It's releasing all of this mineral-rich fluid that's getting solidified into a rock. Okay, so that we've covered everything up to number 5. Let's go on to number 6. How do we make a clastic sedimentary rock? So we're going to kind of focus now on clastic sedimentary rocks because they're probably the most abundant of the sedimentary rocks that we find. And I want to talk more about how they form. So first of all, we have to start with weathering. Okay, so weathering is when you just break down solid rock like bedrock crust into smaller pieces. We're going to actually classify sedimentary rocks, clastic sedimentary rocks, on the basis of grain size. Okay, so if you're very, 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 very small, you're going to be clay. That's like microscopic. Like, think of like rock flour. Like you've ground the rock into flour. It's just very tiny microscopic pieces that forms clay. If it gets a little bit grittier, but it's not quite sand, and we call it silt. And then, of course, you know what sand is. Pebbles are pieces that are greater than 2 millimeters. 2 millimeters about the width of your pencil lead. So think 2 millimeters up to maybe just about maybe 2 centimeters. Then we call that about an inch, right? Then we call that a pebble. If you get bigger than that, and you get maybe like about the size of your hand, we call you a cobble. And if you get even bigger than that, let's say you're about 20 centimeters, we call you a boulder. Okay, and then that's the biggest stuff. The only stuff that carries boulders are glaciers. Glaciers are really good at carrying big pieces of rock. We're going to see that later in lecture number 13. Transport. So the next part, after you get broken down by weathering into either clay, sand, silt, gravel, whatever you are, the next step is transportation. So that's the process of erosion. We created the gravel, but now gravel has to be picked up and carried off somewhere and eroded away. Okay, so a lot of different things do that. Maybe the obvious one you think of is water, right? Like a river carrying the sediment away. But also don't forget wind can also generate, can also transport sediment. And one that we definitely don't think of, especially in Corpus Christi, where we rarely, probably a lot of you had never even really been around snow before, but one that we really don't think of very often is glacial ice. Glacial ice, we're going to see this in lecture 13, is really good at carrying sediment to different places. So after that, we have the process. The next process is deposition. So that sediment is carried off somewhere, it's eroded away, and then it's deposited in like a flat, low-lying valley or something like that, some low-lying basin. But it's got to be low, because remember, this is gravity that's carrying these things. So a low-lying, low-elevation area, the sediment's going to be brought there and deposited either by basically water, wind, or ice. Okay. Now, the last process is something that we call diagenesis. Diagenesis. And that is a really kind of fancy sounding word. What the heck is diagenesis? Let me explain it a little bit more here. You actually have a question there. What are some of the processes involved in diagenesis? So diagenesis, even though it has a very fancy sounding name, scientific sounding name, it's really just a very simple process. It just means the collection of processes that turn sediment into a rock. Okay, so it's the processes that take the sediment and transform it into a rock. Okay, so we go from loose sediment to a solid consolidated rock. All right, so how does that happen? We'll go on there to number 8, talk about processes involved in diagenesis and lithification. So you can imagine here's our river that's bringing sediment in, right? So sediment in, sediment in, sediment in. And what happens is here's our valley, our basin. And of course the river's going to drop that sediment here, and then more will build up on top, and more will build up on top, and more will build up, build up, build up, build up, build up, until we get to the very top, and we've totally filled up that basin now with sediment. Okay, now the basin's kind of complete. Okay, so what happens here? Well, you can imagine that the stuff down here at this low level that's now buried, let's say under a kilometer of material, is under very high pressure. So what happens is that the sediment grains compact because of the pressure. They're going to compact, they're going to squeeze together. Okay, that's going to push out the air. It's going to push out the water, because also along with pressure increasing, as you get buried down deeper and deeper and deeper, your temperature starts to go up as well. So this material is going to start heating up. It's going to start getting higher pressure. It's going to compact together. It's going to squeeze out the water. And when it squeezes out the water or evaporates out the water or drives off the water, a lot of times that water will leave behind natural cements. Now you already know, I showed you this, that a lot of water contains, and look at this already. Can you see how this, remember how I dumped this all together and it was like a white milky substance, and now look at this, it's getting relatively clear. There's still some stuff hanging out actually on top, but it's, I hope you can see it's kind of clarified now. Okay, so that material's come and settled at the bottom. And anyway, my point is, so in showing you that, is that a lot of water contains mineral content, and when it gets driven off or evaporated away, it leaves behind the mineral content, and that can cement together the grains. Okay, so we have the cementation of the grains. Also, there's another thing called pressure solution. Pressure solution. And that occurs when at the grain boundaries, where you have two grains of sediment colliding together and hooking up together, being pressed together, the pressure at the grain boundary, right there, you see where my knuckles are coming together, the pressure at that grain boundary is more intense. And just like if I push my knuckles together like this, I can feel the pressure right there on my knuckles, right? So that pressure is more intense right there where the grains hit. And that pressure helps the grains to dissolve. And they'll actually fuse, and the material will dissolve a little bit to relieve the pressure, and it will be fused and glued together after that. So you can actually glue pieces of rock together just from pressure. Okay, and that's a very common way. It's called pressure solution. It's a very common way of gluing grains of rock together and finishing up the process of diagenesis. Okay. Let's go on to number 9. Talks about for the following minerals, categorize them as susceptible to weathering, or mildly susceptible, or fairly resistant. So, when we talk about weathering and the bedrock breaking down to form sedimentary rocks, some kinds of minerals are going to break down more easily than others. Okay, things that break down very easily are minerals like halite. It's rock salt, right? You know that salt dissolves in water. So if you have a bed of rock salt, it's going to dissolve away really fast. But also calcite. You've seen how calcite breaks down with acidity, right? You see, and you're going to see that even more in the next lecture. Also, olivine breaks down, and plagioclase feldspar breaks down, and pyroxene breaks down very easily. So these are all really highly susceptible to weathering. They break down very easily. Okay. Things that are in the middle are like amphibole, sodium-rich plagioclase, biotite, which is a type of mica. Okay, this is a mica. Plagioclase is a type of feldspar. Okay, this is another kind of feldspar, orthoclase, potassium feldspar. Muscovite is also mica. Okay, so the micas and the feldspars and the amphiboles break down kind of medium, and then things that are very resistant to weathering are things like clay minerals, quartz. I never talk about gibbsite in this class, but hematite I do talk about. Okay, so if a rock breaks down, I want you to think about this. Let's say rocks are breaking down. You got all sorts of different kinds of minerals present in the sediment. As transportation and weathering take place and the sediment is transported down a river, it's getting transported, getting bumped along, it's going to get chemically destroyed and mechanically destroyed. The halite, calcite, olivine, plagioclase, all this stuff's going to break down and disappear. And what you're going to be left with in the end is just clay and quartz and hematite. And actually, when you look at sand, a lot of sand just consists of these things. Quartz, hematite makes it kind of a reddish sand. Sometimes you have some potassium feldspar in there. And that shows you that there's been a lot of processing to that. If you go to the beach, you look at the white sand beach, a lot of that white sand is just quartz. Okay. All right. So now that's a story there on mineral weathering. You have another question there. It talks about list out these clastic rocks from grain size. You know that we classify clastic rocks on the basis of grain size. So if I actually put these things here, we classify them on the basis of grain size. Okay, so boulders are the biggest thing, then cobbles, pebbles, sand, silt, and mud is the very smallest. Mud, aka clay. Okay, so sandstone is made of sand. Conglomerate is made out of pebbles and gravel, right? So that consists of larger pieces. Shale is made out of mud, so made out of clay, so that has the smallest pieces of clastic material. Siltstone's a little bit coarser grain, so it has a little bit larger pieces. Sand has even a little bit larger pieces still. Okay, conglomerates even larger, and breccias. Breccia and conglomerate basically have the largest pieces of sediment. Okay, so I want to finish up here this lecture just talking a little bit even more in depth about clastic rocks and what we can learn by really looking closely at the grains and the shape of the grains. So we can actually glean quite a bit of information about how rocks formed from those grain sizes and from what we call the sorting, the angularity, the grain size, and the maturity of the grains. Okay, so let's first talk about sorting. What does it mean to be well sorted? It means that the sand, or I guess I should say the sediment, consists of a lot of just not a lot of different grain sizes, but just one. Okay, so if it's well sorted, it looks like this. Everything's the same size. If you're poorly sorted, you look like this. You can see that you have some large pieces, some small pieces, some very small pieces, right? So that's poorly sorted versus well sorted. What does that all mean? Okay, sorting can actually tell you two things about how that rock formed. Sorting can tell you first of all, how much transportation the sediment has experienced. If it has experienced a lot of transportation, that means it's been bumped along a riverbed for a long time, or maybe bumped along by winds for a long time and carried very far and processed by the winds or by glaciers or whatever, you are going to get progressively more and more and more sorting. So if you find a very well sorted sandstone, you know that it's undergone a lot of transportation. It can also tell you something about the mode of transport, whether it was by wind, water, or ice. Wind is the best transporter and the best sorter. So very well sorted material comes from wind. Water is medium, ice is the worst. Ice picks up everything from clay to silt to sand to boulders the size of a school bus. And I have seen boulders, literally the size of a school bus, picked up and moved by glaciers. So they're amazing at moving really big pieces of rock. So they're very bad at sorting. Ice is terrible at sorting. Okay. So let's get on to something else. Let's talk about angularity. So think about a rock tumbler, right? If you put a rock in a rock tumbler, it's going to smooth out all of those rough edges, right? So when we find very smooth, let's say we look at a microscope, we look at the grains of sand, we see the grains of sand are very smooth, or the pebbles are very smooth, or the gravel's very smooth. That means that it's been transported for a very long time. It's been bumped along that riverbed for a very long time before it finally came to rest and got diagenesis and turned into a sedimentary rock. Whereas if you find sediment that is very sharp and angular, it means it has not traveled very far before it got consolidated and turned into a sedimentary rock. So it tells you how far away the source of the original clastic bedrock material is. If it's far away, it looks like this. It looks well rounded. If it's close by, it's going to create grains that are more like this, more angular, because it hasn't undergone extensive transportation and all that bumping and rounding that goes on during transportation. Okay, talking about energy, I want to show you this. This is kind of a cool example. This is just a column of different kinds of sediment. And if you take a look at this, what you'll notice is what I did is I shook this up. There's different kinds of sediment in here. And I shook it up and I just let it sit. And you'll notice that the really coarse ground gravel settled out first. And then there's kind of sand on top of that. And then on top of that, there's like silt. So this tells us a little bit about the energy of the environment. It took a long time for that silt to settle out of the water. And it took a little bit of time for the sand to settle out, but the big rocks settled out really quickly. So if I want to stop, if you think about this, if I start shaking this up, well, that silt, you see how the water turned muddy, right? So that silt is now suspended in the water. If I keep shaking this, I'm adding energy to the water. Will that silt ever settle out? And the answer is no, right? As long as there's a lot of energy in the water, that silt will never come out. But you'll notice that the sand and the gravel do. Okay, so what am I trying to get at here? The energy of the water is like the turbulence in the water, how much the water's being stirred up by waves, by tidal action, by river currents, whatever it is. It's stirring up those waters. And if the sediment's very fine-grained, it can't settle out in high-energy water. For silt to settle out, we need silt and clay to settle out, we need to have very low-energy water. So by looking at grain size, we can figure out what the energy, what the turbulence of that water is. So that's pretty interesting as well. Okay. Final thing here is about the maturity of the grains. I already kind of talked about this when we talked about how certain minerals are more resistant and other ones are less so. But suffice to say, if you find a rock that has pure quartz, well, quartz is a really chemically resistant material. If you find it's pure quartz, it means that that material's been processed for a long time by transportation, and all of the less resistant minerals have disappeared. They've been broken down and destroyed. Whereas if you find like olivine sand like this, that's very rare, of course, and it's rare because olivine breaks down really quickly due to chemical and mechanical transportation processes. So when we find green sand like this, it means that the olivine came from someplace really close by. And in fact, you can see right where it came from. There's the basalt cliffs that gave us the olivine sand. It's close to the source, right? That olivine sand came from those cliffs that are just right there. Okay. Whereas if you look at this picture of these quartz sand dunes, you cannot see the original bedrock that quartz came from. It's far, far away. It's undergone a long transport. Okay, so I'm going to finish up now. Your last question on sedimentary structures. Just want to hit on this really quick. Sedimentary structures are just structures that are left in the kind of different forms and shapes, structures that are left in the sediment that tell us something about the environment. A really good example of this are ripple marks. So I don't have my piece of rock here with me, but ripple marks can actually get preserved in the rock, just like you see them here, right? So the real ripple marks that you see at the beach can get actually preserved and fossilized in the rock record. And that tells you a lot of interesting material. It tells you the direction of if there was a river, right? If there was some water flow, that's what creates the ripples. It could tell you the direction of the water flow. It can actually tell you the depth of the water. It can tell you the speed of the water was moving at. So lots of interesting things you can get about the environment, specifics about the environment you can get from things like this. One last little sedimentary structure I want to expose you to are cross beds. So if you look at these kind of interesting pattern, checker mark kind of pattern you see here in this rock, these are called cross beds, and they're actually fossilized sand dunes. So we actually get this information about what the direction of the wind was blowing from looking at this kind of structure in the rock. Okay, so I'll end there because I know I've been going on a long time. Thank you for listening. And please let me know if you need any help with your lecture assignments. So I will talk to you next time, and you have a good week.